All right, let's go ahead and take a look at Chapter 7, Deformation and Strengthening Mechanisms. So what I want to show you before we get started are two tension tests, one for a sample that has low dislocation density and one for a sample that has a high dislocation density. Both these materials are pure copper, and the low dislocation density sample has been annealed, meaning that it's been increased to a high temperature and then held there so that diffusion can help to remove some of the dislocations in the material. And then the high dislocation density one on the right is a sample that's been drawn down to this bar size that you see here, this rod, and all of that mechanical deformation has been left in the sample. And that is the case of a high dislocation density. Okay, so let's go ahead and take a look at these. So we'll go ahead and get these both playing at the same time. And as these are going, you're going to see here that we had a necking. And let's see over here, you're going to see it right there. You saw this necking behavior and then failure. Okay, let me play this one over here on the right again, since this one's fairly short. Again, there's the necking and then boom, failure. So one of the things that you hopefully notice on these is that the delta L here for the elongation to failure is fairly small here on the high dislocation density, and my delta L here on the low dislocation density sample is fairly long. Okay? So the low dislocation density sample is behaving in a ductile way, and the high dislocation density has lost all this ductility. Okay? So we want to try and explain today why this is the case. Why does the dislocation density matter in terms of the ductility of the sample? If we look further at these, we would also see that the higher dislocation density sample is able to have maintain a higher strength and have a higher yield strength than the case for the low dislocation density. So low ductility, but high yield strength. High ductility, but low yield strength. Okay, these two things are always inversely related. So the permanent deformation of most crystalline materials is by the motion of which defect? The answer is dislocation, right? It could be a screw, edge, mixed dislocation. But the answer is just dislocation. All right, before we get started, let's go ahead and take a look at some observations. So we have here the lithium fluoride crystal, which is face-centered cubic, and we are putting an etchant on the surface so that optically we can see features. So the first thing that we see are these pits, okay? And these are four-sided pyramidal pits, right? You can see that. And each of these surfaces that you're seeing here are a 1-1-1 type of surface, right? Remember, these are low energy surfaces. And the center of this surface that we can't see, it's on a much different scale, but this would be the dislocation core coming up to the surface. And so this dislocation core is a high energy, and so the acid etchant etches that dislocation core first, and then as it keeps going deeper, more and more atoms are removed from the sides, and you grow these pyramidal pits. And the reason the 1-1-1 is showing is because that's a way of minimizing the energy of this new area you're creating by displaying or showing the lowest energy planes. Okay. So each of these represents then a dislocation. And then the other thing we can see here is a nice grain boundary running through our sample. Okay. This also has a high energy, and so it also is etched. All right, so we've got a way of visually seeing here dislocations, and we've learned a little bit about where our plane energies actually come into play, and we can see them in real life. So one of the things we want to notice about these pits is that they do seem like they are only in certain directions, right? And we want to be able to explain that today as well. So they're in certain directions, it looks like. They're not uniformly dispersed throughout this sample. And the other thing that you might notice is that they are piling up or seem to be blocked by this they seem to be blocked by this grain boundary. So these dislocations are being formed out here, and they're moving this way. And then as more and more dislocations come in, they're starting to sort of crush these dislocations together because they can't break free of this grain boundary. The problem is that the crystal on the right has a different orientation than the one on the left. And so these dislocations would have to change direction, and that's often difficult to do. And so they get blocked by this grain boundary. Now, one of the things that we want to try and explain is, if these have different spacing as we move closer and closer to the grain boundary, and we said this is because the ones here have much higher stress because all of these dislocations that are here are pushing this way. Well, then they must be repelling each other naturally, otherwise they would just simply collapse on top of each other. Maybe we would have 2 extra half planes or 3 extra half planes, etc. So we'd like to explain also why the dislocations appear to be repelling each other, and that, excuse me, they need a stress in order to push them together. All right, so that's some of our observations. So first thing we can do is ask why or how the dislocations interact with each other. So here we've got an edge dislocation. We can see that extra half plane here. And if we think about the region around this dislocation where the core is, right, it's coming in and out of the board, making the line, you can see that the atoms in here are all closer spaced than they would be if we move away from the dislocation. And so we have more atoms on this side in the space here than we want. So if you want, we could say that the density is higher in this region than it wants to be. And so this is under a state of compression. We have too many atoms for the same space. Well, when these atoms are under compression, what they'd like to do is pull out and have these move a little further away so that they don't have to be in compression. The problem is that the bonds here on these other sets of planes are keeping the atoms close together. But these are stretched outward a little bit to try and accommodate and alleviate some of this compression. So what that does is then create a tension on the bottom part. So the bonds in here should be slightly bigger than they would be in the bulk. Okay. So compression on the side with too many atoms, and the result of that is a tension on the bottom. So if we have 2 dislocations that are approaching each other, and they have their extra half planes on top, then these are like charges, if you want, and they repel each other. At least that's one way to think about it. And they repel each other because if they get close, these compressive stresses will start overlapping, and you'll end up increasing the stress in the sample too high. You need a lot of deformation, and it takes too much energy. And so these want to move away. And the same is true on the bottom. It's just now the tension. And again, as the tension overlaps, they're additive. And so the system doesn't want to do this. So they repel each other. If, for example, we had the extra half plane on the bottom, then this one's going to have the compression then on the bottom, right? The side with the extra atoms, extra half plane. And now these are unlike sign, so they actually attract. Because now this compressive stress in this region is going to then cancel with the tension in this region. Same on the bottom, the tension now is going to cancel with the compression. And so when these come together, right, they're going to annihilate. Now we've got an extra plane, half plane on top and bottom. In other words, we've got an extra full plane. So we do get interaction between dislocations. And what we were seeing in that figure before were dislocations of like sign. All right, so that's trying to address the direction. Why did it look like they were only in certain directions? So when you're trying to slide planes over each other, it's much more efficient and it's much easier if you were to take very highly dense packing planes and move dislocations along those. So if you imagine the 1-1-1 plane for the face-centered cubic, and think of these as billiard balls now, imagine you've got this billiard ball sitting on top of these three, and if you've played pool at all, then you'll know that that ball doesn't sit very deep really at all. So you could push it relatively easily into this site and then back over here, which is where it wants to go. And it doesn't take a lot. If you were to have a plane like the 1-0-0, my drawing's not going to be great, I apologize. Right? So if I have this 1-0-0 plane, I'm trying to draw the other atoms in the other cell, the space that's here, if an atom sits here on the next atomic layer, it's quite big, and this atom would actually sit fairly deep, and it would take a lot more energy to push this thing out and move it into another site. And so it prefers the lowest stress would be on these close packed planes. And to minimize distance as well, we want to move in directions of where the atoms are touching, a high linear density. And so these are all 1-1-0 type directions. Okay, and you can see that in our drawing here, these are all diagonals of a face, right? We learned that all the face diagonals are 1-1-0 types. Could be 1-0-1, 1-1-0, like I wrote here, just to show you that they can have negative signs in here, but all of those types work. And there's 3 of them you can see here for each of the 1-1-1 type planes. Okay. There are 4 1-1-1 type planes. I'll write it as a family now. And there are 3 1-1-0 type family directions that are on each plane. And so this gives you 12 possible choices or slip systems that are active. All right, so that's what this image is trying to show. We've got the face-centered cubic system. We've got 12 slip systems, right? Again, we've got 4 planes, and each plane has 3 directions. All right. Now, if we take a look at the hexagonal close pack system, remember that for the face-centered cubic, we did this ABC packing, and for the hexagonal close pack, we did AB packing. But the atomic packing factors for these were both 0.74, so they're very similar structures in terms of their density and their packing efficiency. But we messed the symmetry up when we changed and went to this AB. We no longer have cubic, but we've got hexagonal. Well, what that's also done is it's placed these high packing type planes all parallel to each other. So these basal planes, and that's it. The other orientations of this crystal don't have these 1-1-1, these are the 1-0-0-0 planes. So they don't have 4 like we would get in the face-centered cubic by cutting off each of these corners. And so our choices become very limited in this system in terms of the slip systems. And so in this case, we end up with only 6 versus 12, plus their spatial orientation is very limited. And so the hexagonal close pack system will behave in a brittle way because we're limited in the movement of dislocations, right? And they're responsible for the ductile behavior, where the face-centered cubics are fairly ductile. All right, if you're reading in your text, the other thing that you'll see is that your text mentions this, and it mentions that because the face-centered is 12 systems and the hexagonal 6, that the face-centered is more ductile. Okay? And that statement's true, but it leads you to think, if you follow that same logic, that the body-centered cubic system, which now has 24 systems, should then be more ductile. Okay, so, and it's not. So your face-centered are your most ductile materials. So BCC is less ductile than the face-centereds, okay, but more ductile than the HCPs. So there's one other piece to the story. The face-centered or 12 directions and their arrangement in space is plenty for ductility. So having additional directions is really not helping any. What else is going on is there is a friction to move the dislocations that we have to overcome. And so there's a minimum energy or minimum stress, a critical stress in order to move them. And for the face-centered system, this critical stress is fairly low because we're moving these 1-1-1 planes that aren't sitting very deeply in each other. And in a body-centered system, the planes sit deeper in each other. And so there's a much higher stress needed to move. And so this critical stress is what dominates in the BCC system, making it less ductile than the face-centered. We'll talk a bit more about that in a couple of videos from now. All right, so this is just showing the HCP system. This is a single crystal of zinc, and it's oriented so the basal plane is just slightly off axis. And you can see now the slip all along these basal planes as they line up all down this crystal. And so that's these planes here. And so that's just neat, kind of a visual of showing this effect. You can never get this with the face-centered, no matter how you oriented it. When you pulled on that sample, it would eventually just neck down and fail. You wouldn't see these bands of deformation like this. Okay, so next time, we're going to take a little break now, and then we'll come back. And next time, we'll start actually looking at the mechanisms of strengthening.